All right, let's start by recapping stoichiometry. The overall idea with stoichiometry is we're figuring out the amounts of either a reactant or a product. In a balanced chemical equation, you're going to have a whole bunch of different reactants and products. We're going to zoom in on just two because a fraction can only have something on the top and something on the bottom, and that's it. So you'll pick the one thing that you know something about, and then the other thing that you pick will be something you're trying to find. So we usually pick B to be the compound that I know something about. So if I have a balanced chemical reaction, it might be something like this. It might be A plus B. Those are my reactants, and they equal C plus D. So in this case, I'm not going to worry about C and D because maybe I know some information about B, and I'm trying to find something about A. So I'm going to zoom in on the reactants. Now you could also, in stoichiometry, use one reactant to figure out something about a product. So maybe B is a reactant and A might be a product. But in this case, let's just say these are both reactants. So say I know maybe the number of molecules of B. Then that's going to go on the bottom of the fraction on the left here. The fraction on the left is all about the real numbers of A and B in real life, in your experiment. So that might be a number of molecules, it could be a number of formula units, or most commonly it's going to be a number of moles. So most of the time we'll be told the number of moles of compound B, and we're going to be trying to figure out then the number of moles of compound A on top. On the other side here, this fraction is all about the coefficients in my balanced chemical equation. So when I balance this chemical equation, maybe I balance it with the numbers 2 and 4 and 3 and maybe a 1 in front of the D, say, when you balance out your equation. It's those coefficients that will go in this fraction here. These coefficients are perfect numbers, so they don't impact your significant figures. When you're using the number 4, that's 4.00000 forever. They have an infinite number of significant figures, so they won't limit the sig figs that you write down. On the other hand, this fraction over here, the one on the left, those numbers are real numbers measured in experiments, so they do impact your significant figures. What you'll do is you'll set up a fraction where the real numbers of A are on top. That's usually the thing you're solving for, so we might call that X. And the real number of B is on the bottom, and that we would put in the actual number. In this fraction over here, we'll put in those coefficients straight from our balanced chemical equation. All right, let's try that with a real example so that it makes a little more sense. Let's say you're combusting 2.4 times 10 to the 5 molecules of octane. We want to know how many molecules of carbon dioxide are produced. So let's assume this is complete combustion. In complete combustion, your balanced chemical equation will look something like this. So we'll start with octane. Octane is C8H18. And we're going to add oxygen to it, right? Remember, in complete combustion, your other reactant is always oxygen. And the two products we get from combusting a hydrocarbon are carbon dioxide gas and water vapor, also a gas. So that's our skeleton equation. Next, we need to balance it. Let's give this a try. We're going to run into some issues in this one because of the odd number of O's from our water here. So the best thing to do right off the bat is just double the number of octanes you have. The issue is going to be that if I were to say put like a 9 in front of the water to balance my hydrogens, I'd have an odd number of O's, and then you could just never make that work out with O2. So I'm just going to double this right off the bat. That means that I'll need, if I have twice as many octanes here, that means I've got 16 carbons. I'm going to need 16 CO2s. Now to balance my H's, I'm going to need 18 in front of the H2 here, so I've got 2 times 18 and 18 times 2. I've got the same number of H's on both sides. And last, to balance out the O's, we've got 16 times 2 oxygens here, so that's 32, plus another 18 oxygens. That makes 50 oxygens altogether on the product side. So 25 times 2 would give me 50 oxygens on the reactant side. So now it's all balanced. So that's your first job. The next move we want to do is to write down this fraction. Now, if I look through the problem, the thing I know something about is octane. So that's going to be the thing that goes on the bottom of both fractions. Super important that you put the same thing in the denominator on both fractions here. On the left fraction, we're going to put the real number of octane molecules from the experiment, which is the 2.4 times 10 to the 25 molecules. On the bottom of this fraction over here, the one on the right, we're going to put the coefficient in front of octane. So that would be the coefficient in your balanced equation, which is 2. On the top, I'm going to put the thing I need to find. So in that case, I'm asked to find molecules of carbon dioxide. So I put carbon dioxide on top. And that means I'm going to be putting the coefficient of carbon dioxide on the top over here. Notice that I can just forget about the oxygen and the water. I'm not asked about those things, so we don't need to figure them out here. If I were, that would be an extra problem. So plugging all those things in, here's what it'll look like. The thing I'm trying to solve for is the number of CO2 molecules, so we'll just call that X because I want to find it. The thing that I know is the number of octane molecules, so I'll put that on the bottom. My coefficients, notice that the thing I'm finding is CO2, so the coefficient of CO2 goes on the top here, right? So the thing on the top is the same on both sides of my equal sign. So 16 is the coefficient in front of the CO2, and octane was the thing I put on the denominator of my left fraction, so the coefficient in front of octane needs to go in the denominator of the right fraction. So 2 is the coefficient in front of octane. Now we're just solving for x. We're going to multiply both sides by the 2.4 times 10 to the 25. It pops up on this side here. And then you can plug that all into your calculator. 16 divided by 2 is 8 times 2.4 times 10 to the 25. It gives me 1.9. I can keep two significant figures because of the two significant figures in the number of molecules of octane. So 1.9 times 10 to the 26 molecules of CO2 would be my answer here.